about the time, basically, to upload the slides, the audit projector slides, that's the reason we just said that it was not uploaded so that we can take notes. Okay, so the exam is on Thursday, right? Are you prepared?
I just got done studying last night.
Okay. Okay, please study for it. It's so important. So your exams are so important, as you know. It carries more weight, right? The exam. So please study very well. Okay. So this is the time you can make up this exam. And if you are behind that, I told you, right? If you are below that 60%, you should be very careful. Okay, you have 2 more exams to go and quizzes to go. So you need to make up with those things, those exams and the homework. So today, there are 3 chapters. I think the syllabus is given 5, 6, and 7, right, for the exam. Yep. But this is also very important chapter, very important, as you can see, that mechanical failures. Why it is so important is, as I always say, as engineers, you need to design the structures which last, not only last, which are safe, right? What are the parameters why materials can fail? And if there is a fracture or if there is a flaw or a defect present in the material, how that can deteriorate. Okay, we are going to see some examples. So they are so important for aerospace. When you hear about the problems with the Boeing and all those things, whenever you decide it, that is the struggle. You need to be very, very careful. And what is another important factor? As aerospace engineers, you should be aware of these things. Another very important factor.
Stress and
strain. That's all right. To check whether your aircraft is well and good. Very important factor. Always remember, regular maintenance, regular servicing. That's what you're going to learn today. Why that regular servicing is important? Okay? Why that regular servicing is important as engineers, you must know. And also, what are the materials you need to choose to design your aircraft, for example? Okay? What are the different, we have already learned that, you see, the transition from the early materials to what we are right now. That's what we are learning. So there can be different types of material. One can be a ductile material, and other thing can be a brittle material, and materials can be in between, and all those properties. So material selection is a very important factor. Agree?
Yes.
Material selection is very important. And defects in a material, you cannot avoid it, right? There can be always some defect. Even the scratch on the surface, that can be catastrophic sometimes. How? We are going to learn today. Okay? So, if you look at this one, what are the cracks lead to failure? Remember the failure, there can be different types of failures, and there is a failure mechanism itself. Okay? How failure propagates, or how cracks propagates through your material. Okay, that's the important thing. Depending on what type of material you have, whether it is a brittle material or a ductile material, you agree that it differs, right? What is the important? Ductile materials are forgiving material. Forgiving material. So, what is the other important term? Forgiving materials, we can get warning. Agree? There is always a warning for that one, for ductile materials. But what happens at brittle material? It fails right away. Exactly. It cracks. It cracks. That's the problem. It fails right away. There is no warning. So the forgiving materials, there can be a warning and all those things. So warning, always a warning is better than a sudden failure, right? So that warning, there is the importance. So this can happen, you know, and what is another important factor, very important factor, the ductility changes with what? Another important factor, environment.
Yeah.
Temperature is one factor, and another factor, environment, what medium, the surface conditions.
Yes.
Do you agree? Because you know that in salty conditions, okay, there can be corrosion and so many other effects. Agree? And whenever there is a corrosion, a pit is formed, right? A pitch, a small hole can be generated, and that small hole can be a defect in your system. Agree? Now, you know, I'm jumping a little forward, but you see a paper, you know, a plastic coated paper. It's not that easy to tear this one, right? Look at this one. It's not that easy to tear it. But if there is already some type of defect in the system, you see, you can easily tear it off. What is the message there? If there is a cut, you have seen that, you know, the snack packs, it comes with a cut. Have you ever thought about it? Why there is a cut? It's easy to tear it apart, right? Whenever there is a cut, you can separate them very easily.
One of the rare occasions where a crack is desirable.
Yeah, that's the, you know, the take-home message is, whenever there is a crack present, with the lower applied stress, you can separate it. That means it can propagate much faster when there is a defect in your system, when there is a crack in your system. That is the message. Okay? Whenever there is a crack or defect in the system, the applied stress can be amplified. It can be amplified. Okay? So you need to remember that. So that's what we will talk about today. So look at this tanker. Okay, this is a oil tanker. I think you know, after the World War II or so, in 40s or 50s, I don't remember the exact time. You know, it split into two pieces. You see, and it was buffeting, and it was, you know, that split was through its girth, and it was buffeting in the sea for quite some time. And the sea with the different temperatures, right? Sometimes the temperature is very cold, sometimes the temperature is not that cold, and all those things. And how it happened is a small crack started on the girth of that ship. And as it buffets through that sea for long time, for so many years, what happens? That small crank expanded, and finally it ended up being split into two pieces, the tanker itself. So the thing is that the reason is, one is the temperature. You know, whenever the temperature changes for your material, sometimes there can be a transition from a ductile material to a brittle material. There can be a transition from ductile to brittle material. Remember that, the temperature condition. So that's what happened in this case. Okay, that's happened whenever the temperatures are low, the crack, the brittleness decreases, and the propagation of the defect, the speed, the rate increases. Okay, that's what happened in this one. So the temperature is a factor, that brittleness is a factor, and so on. This is what happened for that tanker. But if you look at another example, the Aloha Airlines, it happened in 1988 or so, April 1988 or so. And this is also, it was shuttling between Canada and US. All the shuttling service, and there was compression and decompression all the time, right? Whenever there is, you have your landing, and since the hop is a short hop between the places. And that because of that one, that compression and decompression, the fuselage, a small crack. Again, it is in that that it is the coastal area. It started with a corrosion, small defect happens, small pit happens, and as a result of compression and decompression, what happens? Finally, this piece came off. Okay, the whole piece came off because it expanded the whole area, and that piece came off. You understand the importance of this type of defects, right? How can you, as engineers, how can you prevent these things? How can you prevent? Think about it. How can you prevent this type of catastrophe?
Well, the example of like test of points of failure, they low pressure environment to see if it's the standard.
Yeah. Yes. That is in the initial period itself. You need to select the right material, right? Yeah. Yes. You can tell whatever. Yes. Regular inspection, that's a very important factor.
Unless you're Boeing.
Oh, we just go roast Bowen?
Yes.
Yes.
So, yeah, that's the reason I want to give you that important point. The environment, the testing, initial testing is so important. Why that initial testing is important? Because you need to choose the right material. Right material for the right application. That is the whole story. That is very important. Second, regular inspection. That is also very important because you need to find this type of defects in your fuselage. Okay, whenever you have these pieces coming, even the door, you heard about that the Boeing's problem of that emergency door came off, right? Again, it was not inspected. Right? That was a problem. It was not properly inspected at that time.
It was actually a plug door, which doesn't even have any exits.
Bolts there.
Normally speaking.
Yeah. So those are the important factors. And the material properties, these are the very important factors for you as engineers. So, this type of failures can happen, and this basically because of the compression and decompression, okay, within your material, and it is a corrosive environment, and whenever there is a corrosive environment, there can be some pits on your body, and that can propagate whenever you have, what is the meaning of the compression and decompression? That is a cyclic stress. That is a cyclic stress. So under the cyclic stress, these things can happen. That's the whole reason why we study these things. So fracture mechanism. It's a branch of engineering itself, materials and mechanical engineering. So what are the classification of fracture? And you can see the different types of fracture. One is the ductile fracture, another one is the brittle fracture, and then the fracture process, the crack. What are the processes here? Initially there should be a crack formation, and the crack formation is followed by propagation, crack propagation. So again, how we classify a fracture? It depending on the ability of that fracture to propagate, right? That is the ability So this is the ability of material to undergo plastic deformation. And what is the meaning of this one? Plastic deformation?
Permanent
name?
deformation.
Ductility, right?
Correct.
Plastic deformation means ductility, right? Ductility of the material. So what ductile fracture is accompanied by substantial plastic deformation. Here, little or no plastic deformation. And it can be catastrophic too. So, if you look at your sample, you know, if there is a given sample, okay, I don't know whether have you ever looked at your soldering wire, that is the material used to solder, and if you pull it, what happens if you apply a tensile force onto this one? You can see that it is coming out, it is like a plastic, right? And it tapers, and finally it tapers very similar to this one, the first case. Okay? You know, and tapers and it finally comes to a point and the fracture occurs. So then we can say that such a material is very ductile. Say highly ductile material, the fracture happens, you know, the failure happens like this one. It is, you know, it comes to a point where there can be a separation. And these are highly ductile material. And for a moderately ductile material, highly ductile, and a moderately ductile. So moderately ductile material, you can see these type of formation on the surface. Okay, you know, so these type of irregularities on the surface, and when you have a ductile, completely brittle sample, okay, completely brittle sample, what happens? Your ends, these two ends, is like that one. So, how can we define the fracture? How can we define the fracture in simple terms? So we can say that whenever there is a fracture means, you know, imagine that these are two pieces. And these two pieces, you know, you are separating it and there is a fracture. So there should be a static, stress on the sample. or a slowly changing stress on the sample. And it is separated into two pieces. Okay, separated into two pieces under a static stress or slowly changing stress. That is a fracture. And how we can quantify it? How we can quantify this fracture to some extent? And we know that fracture is based on what? The ductility of the material, right? Plastic deformation. Okay, you get it? So plastic deformation and ductility, how we measure ductility of the material? Percentage elongation
or percentage reduction in area.
or percentage reduction in area. Prepare for your exam. Okay, please prepare for your exam. In the last chapter we learned about it, right? Last chapter or the chapter before that we learned about it. What is ductility? Ductility is the percentage elongation or percentage reduction in area. What is percentage elongation? That is the change in length over original length. Or what is the percentage reduction in area? It is the change in area over original area. Right? That is the percentage reduction or percentage elongation. Those are percentage reduction in area or percentage elongation. See, that is the difference. Whenever you have highly ductile, you have this type of high percentage reduction in area or more percentage elongation, and when you have moderately ductile material, you can still see. Okay, what is this? What is this called? Necking. Neck formation. And finally, what you see at these edges, at these sides, is like a fracture which is in the form of teeth. Okay, teeth-like structures. Okay, teeth-like structures at the fractured ends. So here you can see more sharp ends. Got it? So far so good, right? This can be easily seen in cases where you have pipes, and you know that whenever you have low temperatures, you cover that pipes, especially the plastic pipes, tubes and such things. What is the reason? The plasticity decreases with the lowering of temperature. Therefore, as the pressure is applied because of the water or solidification of water, pressure stress increases. As the stress increases, what happens in this case? Brittle fracture happens. Okay, brittle fracture can happen, but what it is shown here is more plastic fracture. Okay, so but the reason why we covered all the pipes, plastic pipes, on a freezing day is because of that one. As the pressure increases, there can be the material is more brittle, and there can be a brittle fracture take place. And you can see in the second case, this is an example of brittle fracture which is shattered into pieces. And very good example is ceramic. What happens if you drop it on a tile, the ceramic plate? It shatters. That is a very good example of brittle fracture. Now, if you look at moderately ductile failure. And I already talked to you about this one. This is the sample and this is the tensile axis. Okay, and initially this is the neck formation. We talked about it. You apply the tensile force onto the sample. Your dog bone sample. You have seen it. We have seen the UTM, the video of that UTM, and you apply the tensile force, and there is a neck formation. Actually, within the material, what happens is you have this type of small void formation. Voids are formed. Small voids are initially formed, and these voids are formed due to what? Because of the breaking of the bones. Because of the breaking of the bones. So if you keep on applying that static force, static stress, what happens? You know, these holes, they coalesce. Agree? Okay, this coalesce. And form this one, a bigger void there, bigger void here, and you see the separation happens. You see, separation happens parallel to the axis, your tensile axis or axis of the sample itself. This is how the separation, right? There is a separation here. You know, if you have that applied stress initially, you know, this is where it happens. So the void starts here, and you see this taking place in this one, and this is parallel to, this is the separation, right? This is the separation. The separation happens parallel to the axis of the sample. Okay? And you know, finally what happens to that sample, if you look at it here, it propagates and finally the failure happens, and look at this shape. And what is this angle to the applied stress axis? What is this angle? What should be this angle?
That is lambda. No, that is phi. Is it phi?
You know, I'm not talking about that one, you know, the what 110 or 50 or 80. What should be that angle? You must remember these things, this is so important. You know, in the future also. 45. Who said 45? Why 45?
45 degrees, because that is the optimal crystal plane angle, because when both, let's see, when both of
Applied
these
stress is 2 times.
2 times
In fact, 2 times, right? The applied stress. Remember that 45 degree. 1, you know, it is basically, it comes from 1 over 1 by square root of 2, cos 45 and cos 4, cos lambda into cos phi. And 1 over 1, the equation is, this is finally comes to 1 over cos phi 45, cos 45 degree into cos, this is cos lambda and the cos phi 45. This, you must remember this. And what is cos 45? 1 over square root of root 2. Cos 45, 1 over square root of root 2. So 1 over 2. This 2. So it should be 2 times the applied stress.
Yes.
It should be 2 times the applied stress. That's the reason why it happens. And remember when I showed you that UTM, I told you, you should be careful. You should see that one. You should remember that. What angle does that crack propagates? Okay, that is so important. So that's the reason why it happens at 45. The lip is, you can see that lip is here the 45 degree. Because that's the slip. You remember there are different planes there, and one of the planes feels the maximum applied stress, and that starts slipping, right? And that's the reason why this 45-degree angle. And you can see that these are the fibrous ends. So this is where you have the fibers. So these are moderately ductile failure. Okay, moderately ductile failure. It's
So always in a test like this where you're just doing a tensile strength like parallel. It's
Yeah.
always in that.
yeah, the parallel, and again we apply that parallel stress, and there are two components, right? Whenever you remember that, right? Whenever the phi is 90 or lambda is 90, what happens? There is a ductile failure. If the planes are perpendicular to that one, to the tensile axis, or parallel to the axis, or perpendicular to the axis, then there is a brittle fracture happens in that case. Okay, and this is basically because in this case it's a moderately ductile failure. It's a moderately ductile failure here, and this is an actual cross-sectional area of your sample. Cross-sectional area, you can see that this is lip is 45 degree, and you can see more grainy structure on the surface, and that is the reason why you have a moderately ductile failure. So you can see this is called a cup and cone fracture. Look at this one. This is a cup. Okay, this part is a cup, and there is a cone. Since this is a cup, there is a cone here. The other side should be cone, and that's the reason why it is called a cup and cone structure. So the cup region, this is shown here, where you can see the spherical dimples, and where the cone, where the lips are, at the lips, you can see the elongated C-shaped dimples here. Okay, so this is spherical dimples here on this side. Okay, at the cup side, this side you can see spherical dimples, and whereas on the other side you can see elongated C-shaped dimples. So this is how you can analyze your failure. This dimple formation is a characteristic of uniaxial tensile failure. Uniaxial tensile failure. So, whereas in this case, you see, for a brittle fracture, completely brittle fracture, look at this one. What you see is not that angular separation or anything like that. You just see two surfaces, and you can see the grainy surfaces on the ends. You get it?
Yes.
The moderately ductile, this is the difference, moderately ductile and the brittle fracture. So this is important, and when NASA, after some problems, after some issues, the first thing they do, or one of the important things they do, is get those samples. Okay, get the failure samples, and the filings and whatever particles you can collect from there. This is exactly what they do, and they analyze it and to learn how the failure happens. Okay, so that's the importance. That's why it's so important for you guys. So they analyze those things, analyze those filings or the particles or whatever left because of that any fracture or any defect happened in your material, and they collect it and they put it under the microscope or scanning electron microscope and look at these type of defects. You know, this is one example, only one example. They look at different, so many other things, but this is one of the things they look at it. What type of failure happens? Okay, and what the surfaces you have, and where it happens, and how it propagated, and so on. That's the importance of these fractographic studies. You know, this is where you have a brittle failure. Okay, you can see that you don't see that this type of cup and cone structures or anything like that. Remember, this cup and cone structure is a characteristic of materials with a moderately ductile failure. Okay, moderately ductile failure, but for the brittle failure, it is like this one. And if you look at some of the brittle materials, you know, you can see, you know, typically for steels, you can see this V-shaped or chevron markings at the point of failure. So the point where it originated, you get, you know, maybe there can be a sand particle here, a sand, and then it propagated, and then you can see all the V-shaped marking here there. And here in this case also it's a fan-like appearance here, and some defect, you know, somewhere here there was a defect and it propagated like this throughout the structure. So this type of failure you can see. And if you look at this one, see, look at these surfaces, and if this is a sample of this type, and what is the angle? This is your tensile axis.
Professor, could you slightly pitch that?
You know, because the problem is this is not the right size here, so it can, whenever I move it, you don't see it. That's the issue. Otherwise, it should be this good. But even in this case, if I move to one side, you know, changes. Yeah, anyway.
I don't really understand the full difference between ductile and brittle failure. Like, is there a certain point where, like, I just don't understand the separation as well?
Yeah, I'm coming to that. Okay, look at this sample. Okay, look at this sample. This is a sample like this one. You are applying a tensile force. And I just talked about it. For a brittle material, okay, brittle fracture, remember in the last chapter or so we learned about it. You know, what is the angle, you know, from that equation cos phi into cos lambda, 1 over cos phi into cos lambda. What happens to that one when it is 90 degree?
Brittle fracture.
Brittle fracture. So it should be a brittle fracture. So brittle fracture, that means it is, you see, in this case, it's 90 degree fracture. Okay, you see, this is a 90, you know, this is, you have this applied stress, and you have that 90 degree, okay, this 90 degree here you have the 90 degree, whenever your stress direction is like this one, and your orientation of the plane is typically like, whatever orientation you can have, but for a brittle fracture, it should be 90 degree, yes?
90 degrees for the not the normal angle, right?
The tensile axis, and you know, the plane, if it is, for example, if your plane is parallel to this one, the most favorable plane is parallel to this one. Assume that this is the parallel. So normal to this one is this, right? And therefore this angle is 90 degree.
Wouldn't normal be pointing up in the plane where it's created an angle?
Normal to the surface is this one, right? Any surface, this is the normal to that surface. So that angle is 90 degree. So that's the reason why you see, you know, this is the failure. What happens? It breaks right away. Unlike the other case, you had an angle there. You see, here in this case there is an angle, right?
Yes.
So that is the difference between the ductile failure and the brittle failure. Okay, got it? I hope you got it, right? Now, these are two terms, important for your quiz. So, transgranular fracture. Transgranular, from the name itself, it's very clear, right? Transgranular means through granules. That's the meaning, word meaning. Through granules, through grains. So that means if the fracture happens through the grain or granules or the particles there, crystals, then it is called transgranular fracture. Okay, and you can see more grainy texture there. You can see more grainy texture for those transgranular fractures. Again, if this is the failure analysis. You take your, wherever the failure happens, take that sample or the cross sections or the particles, whatever you have, collect them and take pictures and look at it whether there was a transgranular fracture or the other one is more intergranular fracture. You see, this is intergranular fracture where the fracture take place through the boundaries of the granules, through the boundaries of the grains. That is called intergranular fracture. Again, from the name, inter. Okay, so at the intersections, or at the intersections means the boundaries. So through the boundaries, the failure happens through the boundaries. That is called the intergranular fracture. Again, you can see that type of fracture here. Under a scanning electron microscope, you can see the surface of that one which is passing through the grains. These are the properties of different types of material. Whenever you have certain material, certain type of steel, you can see this type of failure mechanisms. And these are some of the very good example for the intergranular between the grains in a 3 or 4 steel metal. So you have these things here, and transgranular means it is through the grains. You see this is the grain and it happens through the grain. So these are intergranular and these are transgranular. Aluminum oxide, ceramic, the failure happens like this. Okay? Just to see the difference between the different types of failures. So the principles of fracture mechanics is, basically the fracture strengths are so it has been observed that the fracture strengths are much less than the theoretical strength. You can calculate the theoretical strength of the material, right? If you know the bond energy, and from that one, from the calculation, you can see that you can calculate the fracture strength of the material. And it has been observed that the actual strength of these materials is much lower than that, and it is basically because of imperfections in the sample. Thank you. So that is, the theoretical strength doesn't consider all the defects present in the material. There can be so many defects in your material, right? It doesn't consider all the defects in your material, and that's the reason why the fracture strengths are much less than that of the theoretical strength. So the fracture mechanics, the quantification of the relationship between material properties, stress level, presence of crack producing flows in the system, etc. Flows in the material, etc. That is the quantification of the relationship between the material properties, stress level, presence of crack producing flows in the material, and the propagation mechanism, and so on. So, this enables you to better equip to anticipate and prevent all the structural failures in your system. That is the important. So you need to understand what is the structural relationship, quantification of the relationship between the material properties, stress level, presence, all the interrelationship, relationship between all these factors, that you need to take those things into account. And you can see that even this has been noticed long back. Da Vinci, that is 500 years ago itself, he himself observed that when the rope is longer, okay, this rope length is longer, the chances of failure, when the rope length increases, the chances of failure increases or decreases? Increases.
Can you go back really quick so I can take a picture?
Back to the previous one?
Yes, please. Thank you.
So it basically, because as the length increases, what happens? The number of failures, the number of flows increases. Agreed? Number of defects increases. So as the number of defects increases, what happens to the mechanical strength of that material? Decreases. So he has observed these things back in 500 years ago. So that is the reason why the longer wire, the smaller the load for failure, because there can be a lot of defects in the sample, and it has a larger number of defects. So it can cause premature failure. So from this plot itself, so modulus of elasticity against or applied stress versus strain. Okay, applied stress versus strain, you can see that this is a perfect material with no flows, and when you have a carefully produced glass fiber and a typical ceramic, what is the strength of the material? So the actual engineering material, tensile strength of the engineering material is much less than the perfect material. And remember, there is nothing like a perfect material. There can always be some defects in your material. So, but it is the perfect material here. What meant is the theoretical material without any defect. So, so let me ask you this question in advance. I'm again jumping ahead, but if you have a structure like this, okay, this is where you have a joint, or you know, you have you know, and this or the T-type structure there, and there is another structure. Okay, this diameter and this diameter are the same, okay? Or the cross section, they are the same, and all the other factors are same. So, you know, there is a curvature here, okay, between this one and here, and there is no curvature here. There are sharp ends here. My question is, when you apply a tensile stress onto the sample, some type of load on the sample, which one is stronger?
The one with the curves, the one with the rounded,
Rounded edges.
exactly.
Any other answer? And why this is stronger? Yeah, it's, you know, I'm not saying it's wrong or anything. Yes.
With the first one. It was
First
like,
one?
yeah, it would cause like a brittle fracture, cause it's just straight, like 90 degrees.
The corner.
Versus the other one,
Yeah,
it's spread out.
Yes, again, it's partially correct, you know, that angle and all those things, but with respect to, you know, whenever there is a defect in your system, we are coming to that, but that's the reason I am saying that I am jumping ahead, okay? So any other answer, but I will explain it only after the next few slides, what is the reason, and you can easily see the reason, okay? Any other answer? You know, this is just to make you think. That's the only reason I am telling it right now. I am asking it right now. Yes.
Is it because it's already like shaped in the way that it already wants to move in that direction, so it's easier to distribute our loads. That might be great.
Okay. Any other answer? Yes.
For the curved sample, there's less surface area, so lower concentration of defects along the surface of it.
You know, and we are not talking in terms of the surface area. Okay, not in terms of surface area. We are talking in terms of the angle itself, which I do not want to comment on that one, whether it is, I don't know whether it is correct or not. That's the reason why I don't want to comment on it, whether with respect to that surface area and the defect, what you said, defect is more towards our answer. But about that the surface area, yes, surface area is important basically if you have defects on the surface. Okay, defects on the sample. That's the reason why I'm not saying that it is incorrect, but you know, if there are defects present there, yes, it can be. But other than that, you know, the curvature, that surface area, you know, again, what you said is true with respect to the surface area. When you have more surface or more length, you know, you can have more defects in the sample. But the actual answer is different. Yes.
And then the top one, there's like a weak point in that corner.
Okay.
And then you're kind of transferring that.
Yes. You are coming to that point. That's the reason why I'm asking you. There is a weak, there can be a weak point for the first one, right? And why that is going to be weak, we are going to learn this. Okay?
For the first one, those square corners, they can allow for a higher stress point, and which can then allow for if any defects occur there, it can the corners can more easily allow that defect to propagate.
Yes, these are all correct answer, okay? You're coming towards that real answer, and what is the reason we are going to see in the next slide. So you have the applied stress amplified, for a, forget about this one, okay? I just drew it there, that's all. But applied stress is amplified whenever there is a defect there. And the magnitude of amplification, it depends, how much stress is concentrated and the propagation, how fast your defect propagates, that depends on the magnitude of amplification. And this magnitude of amplification depends on how the cracks are oriented, and its geometry. Okay, and the magnitude of this localized stress diminishes with the distance away from the crack tip, and flows are termed stress racers. Okay, whenever you have a defect in your sample, that defect is called as stress racer. The flows are always termed as stress racers. So now you consider your sample. Okay, you consider your sample. This blue one is the sample, and you consider this as a void or a defect in your sample. This is a defect in your sample. Okay, so you see, this is a defect. Consider this flow as a defect in your sample, and you are applying a stress, and this is the position along the x direction. If you consider that this is the position along the stress direction, and your stress maximum, sigma m, is the stress maximum. You see, the stress maximum is here at the crack tips. These are the crack tips, right? And away from the crack tip, this is the distance. So away from the crack tip, what happens? The stress maximum decreases. Okay, away from this one, the stress maximum decreases, and these are, so therefore we can see as the crack, if there is a crack there and it increases, and at the crack tip the applied stress is maximum. So this is called the Griffith crack. And the maximum stress sigma m, that is the maximum stress sigma m, is equal to 2 into sigma naught into A over rho t, square root of A over rho t. And what is the rho t? If you go to the next one, you can see the equation sigma m. I am writing it again here. Sigma m is equal to 2 into sigma naught into A over rho t. That is square root of rho. This is rho, okay? Rho t. And rho t is nothing but, you can see here, This is that crevices or the floor. And if you take that side, okay, this side, and you can fit a sphere there or a ball here, okay, sphere or ball, and the radius, you know, you can fit it like that one, and the radius of this this ball, okay, that radius of that ball or the sphere, okay, sphere is OT. So, you know, what is sigma naught? Applied stress. And what is sigma m?
Maximum stress.
That is the magnified stress, right? Magnified stress. So, what happens as rho t decreases? Look at that equation. Please look at the equation. What happens as
Stress
you
increases.
sigma m
Increases.
increases?
Just does that.
Sigma m increases as rho t decreases, which means that this is the circle, so this radius decreases. Radius decreases, right? What is the meaning of the radius decreases? You know, just consider this one here, and if you put a ball here, the radius of that ball is the rho t. And you know, you can imagine, right? And as that flow becomes sharper and sharper, what happens to the radius of the ball?
It decreases to zero.
Decreases. So, which means as the crack becomes sharper and sharper, the applied stress is
Greater.
amplified. Okay, amplified more and more. That is the meaning. As this becomes.
I think it rolled off.
Oh.
It does.
Thank you. So that sphere, the sphere as it becomes sharper and sharper, this becomes increases. This increases, sigma m increases. This increases, sigma m maximum stress increases, and therefore, you know, this can be, as this becomes sharper and sharper, it is easier. It requires less applied stress for that crack to propagate.
You mean decrease, right, on the roll?
Where, which one?
The roll on the formula?
Yes.
Decrease, right?
Yeah, sorry. Sorry, this is decreases. As rho t, that is the radius decreases, sorry, this is the radius decreases, this is sigma m increases. So, we can write, so sigma naught is the applied stress, and what is K? Sigma m is maximum stress, okay? Sigma m is maximum stress. What is A? A is, always, please listen here. I didn't define the A. This length of that flow, the total, if the total length is 2A for a completely inside flow, this flow is completely inside the sample. So A is one half of this total length, okay? If it is a completely inside flow, and if it is a side flow, this is the length of this flow, okay? And remember, in the problem, if it is given like the flow is completely inside the sample, you must take one half of that length. If it is on a side flow, okay, then it should be this distance itself, that is the A. So, So the stress concentration factor Kt is equal to sigma m over sigma naught is equal to sigma m by sigma naught is equal to 2 into A over rho T to the half. That is the square root of A. This is A over A over rho T. Okay, so let's stop here and look at it. And now you can answer this question. It is there, it is there in the slides. You can go back and look at it. So please, just 1 second. Look at this one, our previous question I had before. So, in the previous question, now you can answer why this is better, right?
Less stress.
I know, less stress basically because look at the sphere you can fit in there and the road key. So this is sharper and this is much more curved, right? Agree?
Yes.
So that's the reason why you must avoid sharp edges. When you design this material, when you design the structures, you must avoid sharp ends. So these type of edges, the sharp edges should be avoided. So I will just go through the important slides very quickly, but I will upload it so you should be able to see it. It's not, we have already talked about all those slides, but only the very important slides. That doesn't mean that questions are asked only from that those slides. Okay, don't assume it like that. Please don't do that. That may not be the case. So you might get questions from other parts too, but the probability, in terms of probability, you have better chances from here.
We can't see the screen.
That's why we put it in.
So these are some of the slides. The steady state diffusion and the fixed first law is very important. What is steady state diffusion and what is the fixed first law? And the factors affecting diffusion, the temperature, which is a very important factor, and this equation d is equal to d naught to exponential minus qd over rt, and taking the logarithm and solving it, that is important. And non-steady state diffusion. Okay, and what is the non-steady state diffusion? Time dependent diffusion, unlike steady state diffusion. Time dependent diffusion, fixed second law, and this is important. And as well as non-steady state diffusion problems from here, you can expect there is a very good chance of getting problems from this part to solve what is the determined diffusion coefficient or temperature or whatever is required. So in order to do that, you need to know how to take error function. Okay, error function. So that is very important. And how to solve this C, and you may be asked to determine whatever here, X or T or D or whatever you can be asked. So the other one is the diffusion in semiconductors. Okay, what are the different steps for the diffusion in semiconductors? The driving, what is the difference between these two after pre-deposition and driving diffusion? And the next chapter, modulus of elasticity, is also a very important chapter, stress strain curve, and E modulus of elasticity, the change in the modulus of elasticity with respect to materials, with respect to different types of materials, and so on. And you see, this is also a very important slide where you can see force versus interatomic distance. So based on this one, you can determine whether a material is weaker or stronger. what? Slope here, right? Depending on the slope here. And this slope depends on what? Modulus of elasticity. Modulus of elasticity. So you can easily predict whether a material is stronger or weaker from here. The other one is the Poisson's ratio, and then plastic plus the elastic, and so on. And the yield strength ductility is also very important. You see, this is the equation I talked about before. Percentage elongation and percentage reduction in area. Why ductility is important? It is a forgiving structure. Even though the ductile materials may not be as strong as the brittle material, but we prefer ductile material because of the reason forgiving. So toughness is the materials, resistance to fracture if when a crack is present in your material. So we will come back to this one later on, but the different types of dislocations and deformations, slip and slip planes, slip system, and what is the difference between the different crystallographic structures, the face-centered cubic structure and HCP, which one is more ductile and which one is more brittle, and depending on the number of slip systems, which one is more important, more ductile and brittle. So the other one is the twinning, and the difference between twinning and slipping and twinning. These are the two different processes. What is the difference between them, and what is the magnitude? Okay, all these things are important. And depending on the two grains, for example, two samples are given with the two different grain size. Compare that strength of the material. Okay, so questions can be asked like that: small grain size, larger grain size, and why? You know, whenever you have questions, you can see that you need to discuss. If you do not discuss, you will not get full points. Don't expect full points if you do not discuss it. Okay, just say that okay, one is stronger, other is weaker. We are expecting you must know what is the reason for that. That's the reason why that question is there. So whenever you have, as you know, whenever you have a figure there, the graders are so pleased, right? They can see that okay, you know the facts. That's the reason why whenever you include a figure there, it is easy. A figure can talk thousands of words. So the solid solution strengthening. What are the different methods for strengthening the materials? And Kohlberg strain hardening. What is strain hardening and what is the reason? And so on. And what is the other one is this one, the heat treatment. What are the different heat treatment and why you do heat treatment, and all those properties, what happens during that heat treatment, and so on. Those are also very important. So please remember to bring your calculators, okay? And you are allowed to use only your calculator for your without any memory.